Hi, my name is Philippa, and welcome to my Lab 5, The Falling Slinky. Introduction. The goal of this lab is to predict the motion of falling slinky and compare the video analysis and tracker model to a model in GlowScript to see how they compare. Big question, does the bottom of your model slinky stay stationary just like the one in the video? So in the video, the bottom of the slinky does not move until the top reaches it, and then it will finally fall to the ground. Here are relevant equations/concepts that apply to this lab. First, we have drag force and Newton's second law. Newton's second law states the net force acting on an object equals its mass times its acceleration, F equals ma. This means if all forces on an object cancel out, acceleration is zero and the object remains stationary or moves at a constant velocity. Gravitational force is the downward pull on any object due to gravity, calculated as F equals mg, where m is the object's mass and g equals 9.8 meters per second squared, and always goes towards the center of the Earth. Spring force, which is applicable to this because the slinky is a spring, describes the restoring force exerted by a spring, given F equals negative kx, where k is the spring constant and x is the displacement from the spring's natural length. The negative sign means the force always acts opposite to the direction of stretch or compression, pulling the spring back towards equilibrium. In this slinky drop model, all three concepts connect to the gravitational force pulling each coil down. The spring force of the slinky pushes back up, and Newton's second law tells us that when these forces are equal and opposite, the net force is zero, meaning no acceleration and no movement at the bottom coil. Drag force is also an external force that isn't normally accounted for in models, that'll cause the force working opposite against both gravitational and the spring force. Okay, and here we have my tracker model. So the assigned mass I found from just looking up mass of a standard metal slinky. So it's 0.80 kilograms, and the initial position I gained from tracker. And the initial velocity was 0 because the slinky starts from rest. And the video results is that the bottom of the slinky remains stationary until the top of the slinky reaches it. Okay, here we have my GlowScript graph and results. So my ball's mass I got from the internet, same as I did for my tracker. And then my ball's initial velocity is obviously 0 because it starts from rest, and I use the same position vector that I got from my tracker. Gravity, I just sent the gravitational constant, and B, I calculated myself as the drag force. And then in the bottom one, I have my velocity and position update formula as pertained to this model. And then as you can see, my y position versus time graph is similar to my y position versus time graph in tracker. Here is my comparison of real life versus theoretical model. As you can see, they follow similar pathways, however, they're not exactly the same. One is more curved upwards, while one's more of a linear line. Possible errors that could have caused this is inaccurate tracking due to time intervals being very large during tracking. I found that to make tracking easiest for me, I had to increase the frame rate to 8. Whereas the intervals were a lot smaller in my other model, meaning that the data is going to look a little bit different just because one has more data points than the other. And I only started tracking right after the slinky was released, like at the moment that it started moving, well, I guess right before, because velocity was initially 0. So there's no flat part of the model in this. For my results/discussion, we answer the question, why does the bottom of the slinky remain stationary? The bottom of the slinky remains stationary till the top of the slinky meets it. When the drag force acts upon the slinky, the bottom portion begins to fall. The net force on the bottom coil is 0, so by Newton's first law, it remains in static equilibrium. The downward gravitational force mg acting on the bottom coil is exactly balanced by the upward elastic restoring force by the spring force. For the slinky, stretch satisfies Hooke's law. Since the net force is 0, there is no acceleration, and the bottom coil remains stationary until the compressed wave from the released top propagates downward and destroys the equilibrium. Because tension equals gravitational, bottom of the slinky will remain stationary till the top of the slinky reaches it.